can say it is a 3-pulse converter. It is a 3-pulse converter. Okay, and this is circuit for 3-phase half-wave or 3-pulse converter. In that also we have a uncontrolled and controlled, that is half-wave. We are going to see the controlled converter, 3-phase half-wave controlled converter. We have 3 power devices, 3 LCRs are connected with the 3-phase supply R, Y, B, and through the load, that is vacuum motor. And this is the 3-phase half control, that is half-wave controlled converter. And we can say it is a T1, T2 and T3, okay, are connected to the 3 phases R, Y, B with load, R load, and it is connected back to neutral. We are going to see the 3-phase waveform. First we need to draw the supply waveform, 3-phase supply waveform. For the drawing the 3-phase supply waveform, we are going to take the reference axis X and Y axis. In the X axis, we are going to have the reference. Above the reference, we need to draw the 2 reference lines. One is taken as a point A, it is a point A, this point A, and this is 1. Like that, we are going to draw the reference lines below the that is minus point 8 and this is minus 1. Okay, and take the equal divisions as 1 centimeter to 1 centimeter. Now we can draw the 3-phase supply R, Y, B. First we are going to draw the R phase. Take from the 0. We need to connect all the adjacents. This is your R phase. Next, with the first R phase, it is 1 and this is 2 above the reference, and this is minus 1 and this is minus 2 and this is 1.8 and this is 1.8. We need to take the 3 lines above the reference, below the reference. Now we are going to draw the R phase. Just connect the adjacent line, adjacent terminals. Connect all the this is our phase, and the next one is Y 0, 30, 60, 90 and 120. The phases, this is R and this is Y and this is B. Angle between this each is 120 degrees. y phase is 1. And complete this reverse direction. Draw the y phase. Now from this 120, 0, 30, 60, 90, 120. Similarly, find all the terms. Completed the graph in reverse. And this is a three-phase supply waveform. Okay, for drawing the half-wave output. Okay, the output waveform for three-phase half-wave control the converter with R load. Before going to draw the output waveform, okay, we know that the R, Y, B are three-phase are the phase difference of 120 degree, and this is your output current flowing through the load, and this is your output voltage. Okay, output voltage. We are not going to bother about the output current. We are going to draw only the output voltage. For drawing the output voltage, we need to draw the supply waveform. Again, same thing. You take the reference axis. Okay, that is x. Above the reference axis, we need to draw the three lines. One is with 1 centimeter, another one is with 2 centimeter, and 1.8. Similarly, 1 centimeter below the reference and 2 centimeter below the reference and 1.8. And take equal divisions, 1 centimeter equal divisions. Connect all the adjacents, that is a terminals starting from 0 this is R phase, next Y phase 0, 30, 60, 90, 120 from this. The waveform in the reverse direction. RY, the next one is a B. From this 120 is 0, 30, 60, 90 and 120. Complete the waveform in the negative direction. R phase and this is Y phase and this is your T phase and this is supply voltage. Yes, R, Y and this is P naught. Output voltage R, Y. For that we need to give the firing angle. Firing angle we are going to consider as alpha. Alpha is the firing angle. Okay. For that we need to give the pulses to T1, T2 and T3. Okay. We need to give the pulses to T1, T2 and T3. Before that giving a pulses to T1, T2, T3, we need to consider the crossover point. This is a crossover point. What is a crossover point? Crossover point is nothing but after the crossover point, any one of the phase R, Y, any one of the phases going to get maximum. take the reference point. This is 0 point. 0 is the reference point. From that, what is the value of R? R is 0 and Y is negative and P is positive maximum. Okay, and after the crossover point, B is phase is getting decreased. Okay, after the crossover point, the R phase getting increases to the maximum, and B phase is going to become 0 at short time period. Okay, and that is why we are taking the crossover point. After the crossover point, any one of the phases is going to get maximum. Okay, for that phase we are going to give the pulses. Okay, we are going to give the pulses to the T1 first. Okay, the Phase angle we can take alpha 0. First we are going to take the alpha 0, 30 and then 60. Okay. First we are going to take the Phase angle 0. 0 means we are going to give the angle at the crossover point itself. Okay. After giving a pulses to the T1, what happens? The current starts flowing through the R phase and direction T1 and through the load, that is back to load. And what happens? It is going to follow the R phase supply voltage. It is going to follow the R phase supply voltage. Alpha equal to 0. Alpha equal to 0 means it is in that we are going to consider we have a condition that is each thyristor should conduct up to 120 degree. Okay, for the each phase it is going to be responsible to conduct 120 degree. From alpha 0 we are going to consider alpha 0. Then starting from alpha 0 in the thyristor T1 it starts conducting up to 120 degree. 0, 30, 60, 90 and 120. Up to this time period, alpha, that is R phase, is responsible for giving your output. Okay. After the what happens, we are going to give the pulses to Y phase, that is a T2. Okay. Again, T2 starts conducting up to another 120 degree. Okay. From here, Y phase is going to give your output. Okay. After that, 120 degree it is 0, 30, 60, 90, 120 degree. That is responsible T2, and this is T1 is conducting. T1 is conducting, T2 is conducting up to 120 degree. Each is going to conduct up to 120 degree. Okay. Again, from the point, this point, again B phases are going to conduct up to another one more 120 degree. Okay, 120 degree. This is the output waveform for alpha equal to 0. Okay, and we have drawn only the output voltage. Okay. Next we are going to take the output voltage, considering the alpha equal to 60. Alpha equal to 60. Alpha equal to 60 means after the crossover point 0, 30 and 60. From here it should conduct up to 120 degree. Okay. From here the output is going to start. Okay. 0, 30, for the resistive load of wave control converter alpha equal to 30. We can get a continuous output and up to alpha equal to 30. Okay, that is less than or equal to 30. We can get a continuous output voltage. Alpha greater than 30, we are getting a discontinuous output voltage. Half wave controlled converter. Okay. Now we are going to see the RL load. This is for the R load, and now we are going to see the RL load. For RL load, the same supply waveform. Okay, this is for R load. Now RL load. The difference is RL load is we are going to have the inductance. Inductance, what happens to the inductance? It has a continuous current. Okay, we are going to consider that inductance is large. We are going to have the continuous load current. We are not going to get any discontinuous output waveform. Okay, the same RL load, if we are going to consider the feedback diode, that is a freewheeling diode, we are going to get the same output voltage for RL load also. The same output voltage for RL load also. Okay, without the freewheeling diode, we are going to consider up to the 30. We have no difference in the output voltage because all the output voltage are continuous. Then there is no difference. After the greater than 30 degree, alpha 30 degree, we are going to get the output voltage. We are going to draw the same output voltage here. That is consider the RL load. RL load. Okay. We know that we are going to consider the crossover point. After the crossover point only, we are going to draw the output waveform. Okay. After the crossover point, it is the RL load is affecting the waveform after alpha greater than 30 degree. At greater than 30 degree. Okay, we are going to consider the 60 degree. Where is the alpha 60 degree? It is the crossover point. It is 0, 30, 60. From here, we are going to draw the output waveform. That is alpha. Each thyristor should conduct up to 120 degree. T1 is now formed by us. That is more positive. We are going to get the pulses to R phase. We are getting output voltage. That is 0, 30, 60, 90 up to 120. From this point here, we are going to get the output voltage. We are going to get the output voltage up to here. Okay. This is RL. We are getting an output voltage like this. Okay. We are getting an output voltage in the negative also. Okay. In this case, in this RL load, we are getting an output voltage in the negative direction also. If it is more than 90 degree, okay, up to 90 degree, what happens? Up to 90 degree, we can consider this as a rectifying mode. What is a rectifying mode? We are getting a more output voltage in the positive. Okay. Up to this point, we are getting an output voltage. We are getting in the positive. That's a positive. Average value is positive. Okay. Considering the alpha up to 90 degree. Okay. We are drawing the same waveform here. Alpha is 90 degree. What is alpha is 90 degree? This is the crossover point. After the crossover point, 0, 30, 60, 90. We are considering this as 90. Then from here, 120 degree. 0, 30, 60, 90 and 120. 120 degree. We are getting output waveform. What does that mean? We are getting a positive as well as negative. Okay. Output waveforms are equal for alpha up to 90 degree, there is a rectifying mode. Rectifying mode means we are getting output voltage is positive. Okay, whereas alpha 90 degree, output voltage is 0, average output voltage is 0. Whereas more than 90 degree alpha, okay, the output voltage is negative. We can say it as an inverting mode. Okay, it is a rectifying mode. If alpha is more than 90 degree, we can say it as an inverting mode. This half wave controlled converter. Okay. Now we are going to see the RL mode. This is for the R mode, and now we are going to see the RL mode. For RL mode, the same supply waveform. Okay, this is for R mode. Now RL mode, the difference is RL mode is we are going to have the inductance. Inductance, what happens to the inductance? It has a continuous current. Okay, we are going to consider that inductance is large. We are going to have the continuous flow current. We are not going to get any discontinuous output waveform. Okay, the same RL load, if you are going to consider the feedback diode, that is a freewheeling diode, we are going to get the same output voltage for RL load also. The same output voltage for RL load also. Okay, without the freewheeling diode, we are going to consider up to the 30. We have no difference in the output voltage because all the output voltage are continuous. There is no difference. After the greater than 30 degree, alpha 30 degree, we are going to get the output voltage. We are going to draw the same output voltage here. That is consider the RL load. RL load. Okay. We know that we are going to consider the crossover point. After the crossover point only, we are going to draw the output waveform. Okay. After the crossover point, it is the RL load is affecting the waveform after alpha greater than 30 degree. At greater than 30 degree. Okay, we are going to consider the 60 degree. Where is the alpha 60 degree? It is a crossover point. It is 0, 30, 60. From here, we are going to draw the output waveform. That is alpha. Each tie distance will connect up to 120 degree. T1 is now followed by S. That is more positive. We are going to get the pulses to R phase. We are getting output voltage. That is 0, 30, 60, 90 up to 120. From this point here, we are going to get output voltage. We are going to get the output voltage up to here. Okay. It's a RL load. We are getting an output voltage like this. Okay. We are getting the output voltage in the negative also. Okay. In this case, in this RL load, we are getting an output voltage in the negative direction also. If it is more than 90 degree, okay, up to 90 degree, what happened? Up to 90 degree. We can consider this as a rectifying mode. What is a rectifying mode? We are getting a more output voltage in the positive. Okay. Up to this point, we are getting an output voltage. We are getting in the positive. That's a positive. Average value is positive. Okay. Considering the alpha up to 90 degree. Okay. We are drawing the same waveform here. Alpha is 90 degree. What is alpha is 90 degree? This is the crossover point. After the crossover point, 0, 30, 60, 90. We are considering this as a 90. Then from here, 120 degree. 0, 30, 60, 90 and 120. 120 degree. We are getting output waveform. What does that mean? We are getting a positive as well as negative. Okay. Output waveforms are equal Okay, whereas alpha 90 degree output voltage is 0, average output voltage is 0, whereas more than 90 degree alpha, okay, the output voltage is negative. We can say it as an inverting mode. Okay, it is a rectified mode. If alpha is more than 90 degree, we can say it as an inverting mode. Today's topic, we are going to see the power converters. In power converters, it is a conversion of power one form to another form. It is basically these four types. First one is a rectifier, an inverter, chopper, and AC to AC converter. First, rectifier is a converter. It converts AC to DC. And inverter, it is DC to AC, and chopper DC to DC, and final one is AC to AC converter. AC to AC converter has two types: AC voltage controller and cycle converter. AC voltage controller, it is a AC to AC converter without changing the frequency. Voltage is a variable, input voltage is variable, output voltage is also variable. Input voltage is fixed, output voltage is variable, and the frequency is fixed. Whereas in cycle converter, input voltage is fixed, output voltage is variable, and also frequency is also changing. Okay, that is called cycle converter. These are the basic power converters. Okay, in that we are going to see the first one is a rectifier. In rectifier, it is nothing but an AC to DC converter. Rectifier is nothing but AC to DC converter. Okay, input is AC, output is a DC, variable DC. Okay, and based on the AC to DC converter, we have a major first classification is based on the output voltage. Okay, output voltage, one is a controlled rectifier, another one is uncontrolled rectifier. In that we are going to see the phase controlled converter or controlled converter or rectifier. Another one is uncontrolled. Uncontrolled is output is a fixed one. Okay, input is an AC. Okay, input is AC fixed. Output is also fixed, but it's a DC. Then it is called uncontrolled rectifier or converter. The second one is the phase controlled or controlled rectifier or converter. In that we have a single phase as well as three phase. In that uncontrolled also we have a single phase as well as three phase. In this controlled also we have a single phase as well as three phase. In single phase controlled rectifier we have a semi converter and full converter and dual converter. Same thing, we have a three phase controlled rectifier. We have a semi converter, full converter and dual converter. Okay. First we are going to see the single phase converter. That single phase converter, we have a further two more classification. One is full wave, another one is half wave. Okay, in that single phase controlled rectifier or converter, we have full wave as well as half wave. In that full wave, okay, we have further more classification. One is a midpoint, another one is a bridge type. Okay, midpoint type and bridge type. In midpoint and bridge type, we have a